welcome to the course Advanced Reaction Engineering. So, in this course we already discussed about the bioreactors. So, today we will discuss about the bioreactor, that is chemostat. So, it is used it is one kind of CST reactors. In that particular reactors it contains microorganism. So, thence it is called chemostat or bioreactor you can say. So, in these details about these reactors we already have discussed about the chemostat reactor. So, how to means what are the feed lines, these are the component means sterile medium that are used, this is the reservoir or here it is present, and then it is feeding by controlling some controlling units or flow control valve is there. With that we can change the feed rate that is inside coming, that is inside of the reactor, that we can control volumetric flow rate. So, then once that reactant come out inside of the reactors with the microorganisms. So, here nutrients other components should be there, and at the same times with the help of the compressed air cylinders or from the rotameters. So, air may be supply inside of the reactor from the bottoms of the reactor through the sparger, and here paddle blade is also there. We can adjust the pH also inside of the reactors when bioreactions will take place inside of the reactor, and outside of the reactor cooling water supply is in, cooling out water outlet is there. So, by that way you can maintain an isothermal temperature, let us say 35 degree centigrade is required for bioreactions for a particular microorganism. So, then that we can maintain, and once the reaction is over, then the product we can take out from the bottom of that reactors. So, here question is how to control the cell growth rate, means suppose everything is known. So, means the concentration inside of the reactors, the means when substrate cell is there. So, then concentration of the cells gradually will increase. So, if we continuously want to get means get the products by increasing the cell growth rates or decreasing the cell growth rate. So, how that we can control that? We can control the feed line or that is feed entering volumetric flow rate if not 0. So, by controlling this we can increase or decreasing this, we can control that. So, it actually help us the cell growth rate. How we can do that? By controlling the volumetric flow rate or adjusting the volumetric feed rate or dilution rate you can say. So, that we will discuss basically today. So, here's number 1 is the washout conditions when the cell concentration is 0 and the maximum cell production rate CC max means maximum concentration of the cells that would be inside of the reactor, and when concentration of the cell concentration inside of the reactor would be 0. So, if we control the volumetric flow rate or feed rate in the reactor if it is continuous mode. So, then how we can control that? Here D is the dilution rate, DCC, that is the maximum rate of cell productions. Here CC is the cell concentrations, D is the dilution rate. So, if we know dilution rate and cell concentrations, so then multiplied with that maximum cell production rate we can find out. And what is the dilution rate or capital D? Capital D is the V naught by V. V is the volume of the reactor and V naught is the volumetric flow rate. So, in a reactors you can see, so here V naught particular flow rates it is entering, and if in volume is specified, V is specified. So, then the dilution rate or D we can find out. So, D equals to mu, that is the specific reaction rate constant. So, how it is? So, that things we will discuss actually. So, here the definition of the dilution rate V naught by V unit is hour inverse or time inverse. Okay. So, now in the design equation when the bioreactors we have studied. So, there are components present in the cell, that is the reactor is the cell substrate. So, cell balance as per the cell balance for a CST reactor. So, we have discussed this is the cell balance equation, general cell balance equation 1, and for the substrate this is the general mole balance equation, material balance equation for component substrate that is being used for the cell reactions. So, this is already we have discussed, that is the dilution parameters or D, what is D. Okay. So, now from these two equations means this is unsteady state conditions or cell balance equations or cell mass balance equations and substrate mass balance equations. So, in this design equations, equation 1 and 2 if we divided by volume. Okay. So, this was the equation 1, equation 2, both the equations, if the equation 1 dividing by V. Okay. Here also dividing by V, capital V, that is the volume of the reactors, if we divide by the volume of the reactors. So, then at the beginnings we are assuming that the cell concentrations is 0. Okay. And then if this is the input terms, this is generation terms and this is output terms and this is accumulation terms. So, these equations means if we assume that initial concentration of the cells that was 0. So, then these equations after dividing by volume. So, this would come, equation 3 will generate dCc by dt equals to 0 minus dCc plus Rg minus Rd. So, d is the dilution rate, this is given here V naught by V, and Cc is the cell concentrations, Rg is the rate of cell formations and Rd is the rate of disappearance of the cells, that is the dead cell. Okay. So, this is unsteady state mass balance for the chemostat for cell. Okay. And similarly for substrate also material balance we can do, and from that equation 2 if we divided by V. So, then the equations, general material balance equations would be this, and it we can write this way. Okay. So, here V by V naught we are substituting or replacing with respect to the D, capital D. So, then this equation 2 or equations would becomes this. So, now at this is finally we are getting after rearranging this equations is this. Okay. So, equation 3 and equation 4, equation 3 is for cell unsteady state material balance and this is for substrate unsteady state substrate balance. Okay. For the chemostat or the reactor that we are using, material balance for cell and substrate, that is we have. So, now from the monod equations for bacterial cell growth rate. So, we have studied that is Rg equals to mu into Cc, that is the cell concentrations and growth rate constant, and then maximum mu max Cs Cc by Ks plus Cs. So, Ks is the monod constant and C is the substrate concentrations, cell concentration, substrate concentration. So, this is the definitions of the monod equation for the bacterial cell growth. So, now if we want to conduct the cell reactions inside of the chemostat at steady state, when steady state is there, then there is no accumulations at the beginning. So, when reactor was empty, so then at a particular volumetric flow rates components means cell substrate is coming, it would be fill up gradually, and once it is fill up then system should be steady state, flow will start. So, at the beginning it was unsteady state, once it is fill up and then coming out at the same flow rate. So, then system is steady state. So, at steady state there is no accumulations. So, then this part we can eliminate from the equations, cell balance equation, equation 3, and from then after rearranging these equations we can get dCc equals to Rg minus Rd. Rg is the rate of formation of the cell and Rd is the rate of disappearance or dead cell, means the rate of means after stationary phase the cell gradually means deads. So, then we have to subtract this. So, that we already have discussed. So, that is coming from these equations, and for the substrate also we can write these equations. This was the substrate balance equations, material balance equation or mass balance equation for the chemostat. So, then at steady state this part would be 0. So, that we have written here. So, then after rearranging these equations would become this, and these equations would become this at steady state. Okay. So, at steady state accumulations part would be 0. Okay. There is no accumulations in the system. So, the inlet outlet flow that is maintaining. Okay. And there is some cell reactions would be there, that is cell growth, substrate consumption, that part will take place continuously. So, now equation 6 and equation 7 we have. So, these are the two equations we have, for one is the cell, another one is the substrate. So, now in this equation 6 R d, that is part cell death rate, if we assume that when we have started the reaction. So, cell death rate is 0. Okay. So, then this part we can substitute here, and R g equals to mu into C c, that is the rate of cell growth rate, that is the definitions that we have discussed in our previous class. These are the two things we can substitute here in the equation 6. Okay. So, now at steady state mass flow rate of the cell out of the systems is F c. F c is the molar mass flow rate for cell, okay, mass per unit time. So, here if we know the volumetric flow rates of the feed and cell concentrations, if we multiply that, then gram cell per unit hour, that is the mass flow rate of the cell, since molecular rate is not possible to measure. So, it is expressed usually in terms of the mass rate, and if this is equals to R g into V. R g is the cell growth rate, if we multiply it with the volume of the reactor, then that would be the mass rate of the cells that is coming. Here R g equals to, by definition, is this mu into C c. So, if you substitute here, so then it would become this. Okay. So, now dividing both sides C c by C c into V, if we dividing in these equations by C c into V. So, then here also C c V, here also C c V. So, then it is coming this from here and this is here. So, from here, so if both the side, left hand side and the right hand side, if we divide with C c into V. So, then this equations is coming V naught by V equals to mu. So, V naught by V is the D. Okay. So, that is the equation 8. Okay. So, means D is the dilution rate and mu is the specific rate constant for cell growth. Okay. So, how they are related? So, this is D equals to mu. Okay. So, both having time inverse, that is the units. Okay. So, now here D equals to mu, that we have means developed by steady state mass balance for the cell of the systems. So, now we know the cell growth rate, that is the red equations, and monod equation that we know. So, here we are substituting mu in terms of D. Okay, here we are substituting with D, and then we are rearranging. Once we rearrange these equations, so then the equations, see here, this is the substrate concentrations, this is also substrate concentrations. So, that would be become in left hand side substrate concentrations equals to D into Ks, that is the monod constant mu max minus D. So, if we know or want to find out the substrate concentrations, then what are the things we have to know inside the reactors? If you know dilution rate, constant, these are the constant if you know, and D. So, D value we can change. So, what is the definition of the D? D is the volumetric flow rate by volume. Volume of a particular reactor is the constant, but volumetric flow rate, that we can change. Volumetric flow rate we can change. Volume is the constant for a particular reactors. Okay. So, this part is variable. So, if we change this V naught, if we increase, D will increase. If we decrease V naught, volumetric flow rate of the feed that is entering inside of the reactor, so then D value will change according to the V naught. Okay. So, by this way, inside of the reactor for a particular reaction systems, from the monod constants, these are the constants if it is known. So, then substrate concentrations we can vary inside of the reactor by changing this dilution factor or D. So, if we change increasing or decreasing the molar flow rates, volumetric flow rate of the systems that is coming or entering from the inlet of the reactor, so then substrate concentration we can change. Okay. So, now as per the definition of the substrate, so the red equations we have discussed in your previous class, minus R s, that is the rate of substrate disappearance, that is equals to rate of means cell formations as well as cell maintenance, the amount of the substrate being consumed, that would be the rate of substrate disappearance. That way you have written, and yield coefficient also we have discussed in our previous class also. So, yield coefficients substrate and cell we can express this way, and for the cell concentrations we know C c equals to yield coefficient cell and substrate, and the substrate concentration difference initially and finally at any time Cs is that at T times cell substrate concentration, and this is T equals to 0 or times substrate concentration. So, cell concentration if you know yield coefficient and substrate concentration initially and at the end, then we can find out this. Okay. So, here see these definitions is this same, okay. And here in these definitions we can write this substrate concentration. If we neglect the cell maintenance terms, so then minus R s equals to R g into Y s c, okay, yield coefficient and cell growth rate, then substrate consumptions we can find out, and this is the cell concentration. So, here substrate concentration we have find out. This equation 9 if we substitute here in this equation 10 Cs, we are substituting Cs from equation 9. So, then we can get this equation 11. In the equation 11 left hand side is the cell concentration and here is the substrate concentration. This substrate concentration we are substituting here. So, then cell concentrations as yield coefficient, substrate concentration at the beginning, dilution rate, Monod constant and D. So, here this is the design equation for cell concentrations. So, and here D is the dilution factors, it has a D equals to mu, it has a units, power time inverse, hour inverse or minute inverse or second inverse, depending upon that rate we are taking, means volumetric flow rates, that dmq per minute, dmq per second, dmq per hour, based on that the time inverse will come, that is the dilution rate or factors. Okay. So, now using equation 11, that is called the design equation for that chemostat or the bioreactor. So, cell concentrations if you want to know at any time. So, then dilution factors D is volumetric flow rate, how we are maintaining or changing for a particular reaction system, that is in our hand or that is in our control. So, if you these are the constant terms, these are the fixed for the particular systems, YCS is also fixed. So, then substrate concentration, how much initially you have charged inside of the reactors, that if you know, then what would be the cell concentrations. So, if we change or vary V naught, that is volumetric flow rate. So, using these equations easily theoretically we can find out the cell concentration at any time. If we maintain that particular flow rates for a particular dilution rate for a particular chemostat or microorganism or bioreactions. So, the inside of a chemostat or bioreactor, then at a particular time what would be the cell concentration, that we can find out. Similarly, substrate concentration we can find out using equation 9. Okay. So, substrate concentration and cell concentration at any time inside of the reactor when bioreactions is going on, theoretically using equation 9 and equation 11 we can easily find out. Okay. So, here just we have to put the dilution factor D factors or dilution rates, that we have to put it here. Okay. So, now we are going to find out. So, means when a system is there at a particular volumetric rate, substrate is entering inside of the reactor and then at a particular volumetric flow rate after reaction cell substrate it is leaving from the system. So, here this volumetric flow rate we can increase like that dmq per second, that way we can increase or decrease. If we increase, what would happen after a certain period of time will come when the cell concentration inside of the reactors would be 0. So, that is called washout condition, means almost all cells that has been developed here or formed here in that particular reactions conditions. So, due to the means this feed rate, almost all cells will leaving from the reactor. So, here cell concentrations would be 0, or maybe by changing this, here cell concentrations CC maximum, means the highest concentration should be there, means 0 to maximums. How we can control cell concentration inside of the reactors, that we will discuss basically. Okay. So, cell concentration how can when cell concentration is 0 inside of the reactor, then it is called washout, means almost all cells left from that particular reactor. So, that depends on dilution factor or D. So, that things we will discuss. So, from the material balance equations we know this. So, if there is no inlet, this part is 0 and by definition is this, and RD part is 0, means we are assuming that there is no death of particular that cell is not there, RD part is 0, and RG, that is the cell growth rate, that is mu into Cc. So, in this particular equation or material balance for a C star we have developed this. So, here we can substitute Rg equals to mu into Cc and D part 0, and if we take common Cc part, then dCc by dt equals to mu minus d into Cc. Okay. So, here in this particular equations, mu minus d into Cc, that is the right hand side is there. Okay. So, here if mu equals to d, let us say, then this is the concentration change would be 0. Okay. If we put mu equals to d, then this right hand side part would be 0. So, if d part is greater than mu, so then this dCc by dt equals to negative, this part would be negative right hand side. If d is higher than this, under these conditions this rate of cell changes, concentration of the cell changes per unit times would be negatives. If d greater than mu, means mu is greater than d, so then dCc by dt would be positive. Okay. Rate of formations will increase. Okay. So, then by controlling this d, either mu equals to d, d greater than mu or d less than mu. So, under these conditions, so let us say if d greater than mu, in these conditions dCc by dt, the changes of the cell concentration per unit times would be negative, means cell concentration will continue decrease until we reach a point all cells will be washed out from the reactor, means cell concentrations will be 0. Okay. So, means if we change d such a way that means d greater than mu, means mu has a certain value, let us say it is 10, and d value is, let us say initially you have taken 20. So, by that if we gradually decrease that value, increase that value. So, then if we increase that value, d value 20, 25, 30, 40, 50, like that way, if we increase this value, then the cell concentration, if we are increasing d value, it means V naught by V. So, it means V naught value we are increasing. If we are increasing d dilution rate, it means volumetric flow rate, that is the entering inside of the reactors or from the inlet point of the reactor, that we are gradually increasing. So, d is increasing, when d is increasing at a certain period of time, that what would happen. So, almost all cells that would, if we increase this value, so then cell was there inside of the reactor, so that would leave from the reactors. So, then there would be no cell, living cells left inside of the reactor, Cc concentrations would be 0. Okay. So, these conditions is happen sometimes, so that depends upon the d. Okay. So, cell concentrations when would be d 0? So, from these equations, from equation 11 we have discussed, this equation cell concentration we have discussed. So, this is the cell concentration at any time. So, when this Cc value would be 0. So, if we put Cc equals to 0, so this part equals to 0, then after rearranging we can get d max equals to mu max into Cs 0 by Ks plus Cs 0. Cs is the substrate concentration, that is the initial concentration, and mu max is that monod constant, and Ks also monod constant. So, monod equation constant. So, then d max, d is basically nu 0 by V, that is the d max. So, means maximum volumetric flow rates what we have to maintain, then cell concentrations would be 0, Cc would be 0. So, this is the conditions we have to maintain for that washout conditions. Okay. So, now to determine the maximum concentrations, means from the washout conditions, cell concentrations at what d dilution rate, maximum dilution rate or volumetric flow rates, we can change the cell concentrations to 0 inside of the reactor. So, that we should know. Now, we are going to discuss when the cell concentration would be maximum, means when cell concentration would be 0, when cell concentration maximum, that also we should know. So, then we are going to discuss to determine the maximum cell productions rate inside of the reactor, that is very important also. Okay. So, the cell productions rate per unit volume of the reactors, that is the mass flow rate of the cells out of the reactor, that usually we can express in terms of m dot c, that is the mass rate of the cell, that is the concentration Cc into V naught. V naught is the volumetric flow rate. So, Cc is the, what is the unit of the Cc? Gram cell per dmq, and volumetric flow rate, that it has unit dmq per unit time or hour. So, this dmq is cancelling out, gram cell per hour. So, this m dot c, that is the gram cell per unit time, okay, that is the units, mass rate of the cells per unit times we can get this way. So, in these equations, if we divided by the volume, that is the volume of the reactor, so then Cc V naught, if we divided by this, it would coming d into Cc, since V naught by V, that is equals to d. Okay. So, then it is coming this, and the design equations we had this. So, we have discussed equation number 11, that is the design equation for that bioreactors or chemostat. So, here in these equations, if we substitute this Cc, we have from the design equation, this we are substituting here, then dCc in the left hand side, right hand side d remain there, Cc would be this. Okay. So, we are writing this. Okay. So, then here d is the dilution rate and dCc, that is the maximum rate of cell productions. So, here in the left hand side is the dCc, that is the maximum rate of the cell productions. Okay. So, maximum rate of cell production, this is the both in a single component, and that is the maximum rate of cell productions we can write, or that equals to right hand side is, these are the components. So, if we know dilution rate, yield coefficient, substrate concentrations, and these are the coefficient in the Monod equation. So, then if we put in the right hand side of the equation 5, then in the we can get the maximum rate of cell production inside of the reactors. Okay. This is the maximum rate of, and this equation is the maximum concentration of the cell inside of the reactors and maximum rate of cell productions. Okay. So, in these equations, okay. So, just multiplied with d, what would coming, that is we are saying that maximum rate of cell productions. Okay. So, now if we have, suppose we have a reactor, bioreactors, and inside of the reactor we are doing the cell reactions. So, we have data, means from the experiment d Cc and d we can control, d equals to, what is this, d equals to V naught by V. So, at different volumetric flow rate, dilution rate we can 1, 2, 3, 4 like that way we can find out. If we set a particular run d equals to 1, then dCc value will get. Similarly, for dilution rate equals to when 2, then dCc cell production rate will get this. Similarly, if we set another set of run, dilution factor d is the equals to 3, then corresponding dCc would be this, like that in number of 10, 20 number of means experimental data point we can find out, and if we plot them, means x axis d and y axis dCc we are plotting. Okay. So, x axis we are plotting dilution rate and y axis we are plotting maximum rate of cell production. So, that we are writing, okay, in the left hand side, and x axis and y axis we are that way. So, then once we plot the data, then we can find that cell concentration would be like this and dCc would be like this. This is the dCc part actually. Okay. So, cell concentration, this is production rate, it would come like this, and cell concentrations would vary like this, and substrate concentrations inside of the reactors it would be like this. Okay. So, then we can get, if we dCc against d, if we see it is coming going maximum cell production is here, and then it is gradually decrease. So, this is the d max, this particular point. So, this particular d max means d means V naught by V. So, maximum, then this is also max. So, this way means when we maintain that particular dilution rate, then we can get maximum rate of cell productions at this particular points. Okay. So, now we have equation this 5, equation 5 we have developed this equation 5. So, equation 5 if we differentiate with respect to the d and put 0, means this equation 5 we are differentiating with respect to the d and putting left hand side 0. So, thence whatever the right hand side is coming, so that would fulfill here this part, actually here slope equals to 0, dCc by dd equals to 0 at this particular point. Okay. So, here would be the maximum dilutions rate when cell concentrations or the cell productions rate would be the maximum. So, if we equation 5 if we differentiate with respect to the d and put 0, then this particular point would come. Okay. So, after differentiating if we rearrange these equations, so then it would be like this. Okay. Equation 6 would come. So, maximum cell productions that is coming, that equals to mu max into 1 minus square root Ks by Ks plus Cs 0. So, using equation 6 also directly we can find out that when the maximum cell production should be there, dCc would be maximum. So, then if we know substrate concentrations, monod constant Ks and mu max, if we substitute in equation 6, then maximum dilutions rate or maximum productions rate of cell productions in that particular reactor we can find out by using equation 6. Okay. So, if we substrate concentrations, if we plot with respect to the d in this equation 9, you can see d is there and C is the Cs is the substrate concentration, d is the dilution rate. In the x axis if we put d and y axis C is S, if we plot, then as per equation 6 it would be following like this, substrate concentrations will follow with dilutions rate is like that. And if we want to know the cell concentration with dilutions rate, I said this is equations from equation 11's cell concentrations and dilutions rate, how does it look like. So, then if we plot them, so using equation 11, so if we know at a particular dilution rate what would be the cell concentration if we put all other known components. So, then if we plot Cc and d is like this. So, if we increase the dilutions rate d, then cell concentrations inside of the reactors will be gradually decreasing. Okay. So, this is the different equation, or we have developed or we have discussed different equations how we can find out the different cell concentrations and substrate concentrations. So, here many examples are this type of bioreactions may be there. So, where this is the bioorganisms that is we can use for a particular reaction, that is the sucrose as a substrate. So, for a particular these cells to chemostat or the reactor volume. So, then it is as a substrate and this is the cell, and if we conduct the reactions in a reactors that is having volume 10 dmq. So, in that particular reaction system, so what would be the cell concentration, what would be the substrate concentrations, what would be the productions rate of cell productions rates that we can measure at steady state by considering different dilutions rate. So, if we change dilution rate, the cell productions rate, concentration of the cells, substrate concentration inside of the reactors, that way also we can express or we can control the reactor systems. Okay. So, today is up to this, means what we have studied. So, today basically we have studied that is the washout conditions when cell concentration would be 0 and maximum cell productions rate, that is the dCc. So, in this means washout conditions means dilutions rate, what is dilutions rate, that also by definitions we have discussed. So, now we developed few equations. So, theoretically means without conducting any reaction. So, we can find out for a particular or specific reaction what would be the substrate concentrations and what would be the cell concentrations. Okay. And at washout conditions d equals to d dilution rate, at washout conditions for dilutions means what would be the dilutions rate. So, that also or maximum dilution rate when cell concentration would be 0, that from equation 4 also we can determine. And at the same time by using equation 5 also, so we can say that what would be the maximum cell productions rate inside of the bioreactors we can find out. So, okay. So, these are the equations are useful. So, I hope it is clear for you. means and bioreactor part is also over. So, then next day we will start something different. Okay, so non isothermal reactors we will study. Thank you.